Hello, welcome back. The title of this lesson is called Solving Right Triangles, and this is part one. So in the last several lessons, we have learned how to really use sine, cosine, and tangent, the trigonometric ratios. We've also learned a lot about the unit circle in degrees and also in radians. And we've learned how to go backwards, how to take the inverse sine, the inverse cosine, the inverse tangent, and we've learned about all of that. So that should be tools that you already have with you. Now we're going to start to apply all of that to practical situations. So here we have a section called Solving Right Triangles. So what we mean when we say solve a right triangle is we want to figure out all of the angles and all three of the sides of the triangle. If we know all three angles and we know the lengths of all three sides of the triangle, then we're said to have solved it. That's what we're trying to do. So before we jump into the right triangles, let's just draw a general situation because we're going to be doing work with this sort of triangle later on. Let's take a general triangle that is not a right triangle. So this is not a right triangle, but you might have a three-sided figure. We call it a triangle, and we have capital A, that's angle A here, capital B up here, and then capital C over here. And the way that we normally do this is the sides that are opposite to these angles, we use the lowercase. So for A, we have lowercase a, that means this side. Opposite B, we have lowercase b. Opposite, we have lowercase c. Of course, lowercase and uppercase c look very similar, so you have to make sure that c is smaller. So we could put the angle measures in here. I could put the angle marks here, and you can do that. But when you draw enough triangles, you stop doing that after a while. And you know that capital letters on the corners are the names of the angles, and the lowercase on the sides of the triangle, those are the lengths of the sides. All right. Now, this is a general triangle. It's obviously not a right triangle. Now let's draw a more general situation. Let's say we have a triangle. So I'll kind of like go down below here. And I'll say that instead of a triangle like that, we now have a proper right triangle. Now, the right triangle can be drawn any direction you want, but the thing that makes it a right triangle is that you need to have at least one 90 degree. You have to have one 90 degree off there in the corner. This makes it a right triangle. But we have sort of the same situation. We can name this angle A, and we can name this angle B, and we can name this one angle C, and we have the same sort of situation over here. So opposite angle A, we have side A, and we have opposite angle B, we have side B with a lowercase, and opposite angle C, we have side C with a lowercase c. All right, now we know from what this marking means that angle C is 90 degrees. And that's what makes it a right triangle. So this little square in the corner means that this is 90 degrees. So you already know one of the three angles in this triangle. So when we say that we want to solve the triangle or solve the right triangle, what we're asking ourselves is we want to know the measure of angle A, the measure of angle B up here, and also the measure of angle C. Now in this case, we already know what C is, but we would need to know all three angles. And then the length of side A, the length of side B, and the length of side C. So in this lesson, we're going to focus on solving triangles. I'm going to give you some sides and some angles, and we're going to have to use what we know to find all the other sides and all the other angles for a right triangle. Then we're going to do applications where we use this for word problems to triangulate things and calculate things in real life. That's why we learn this stuff anyway. And then later on down the road, we're going to solve general triangles, which are not right triangles, and they're a little more tricky to solve. Right triangles, fairly easy. General triangles like this, a little more difficult. We are going to cover that in a later lesson. All right, so let's jump into problem number one. So now that we know what we're trying to do, let me just tell you that I'm going to give you the measure of angle A to be given to you as 36.2 degrees. And I'm going to tell you that the length C of this triangle is 68. Now 68 what? It could be 68 centimeters, 68 meters, 68 light years, whatever. 68 some distance unit. And here we have degrees. Now it's a good idea when you do this to draw a picture. What we're trying to solve for to finish the problem is to find the measure of angle B and the measure of angle C, and then also the length of side A and the length of side B, basically the four values we don't have. So what we want to do is we want to draw a figure that exactly mirrors the situation here. So we draw our right triangle like this, and you can draw it either way you want, but I'm going to make it look exactly like the one we have here. So this was A and B and C. So I'm going to write that down. I'm going to say this is A, and this was B, and this was C, and then that makes this one A, and that makes this one B, and this is lowercase c. And then you should probably put in what you actually know. So we know that the length of the C side is 68 units, and we know that the measure of angle A right here, so I'll just put like a little equal sign down here, 36.2 degrees. That's kind of the angle measure of A right here. So how do we figure out the rest of the problem? Now, the first thing you're going to learn is that there's always more than one way to do a problem. So what I'm going to do is solve it for you the way I did it. And then you might say, well, I would do it in a different order, and that would be fine. As long as you're getting all the same answers as me, that's fine. So let's take a look at this and think about what trig information or what trig functions we can use to help us solve the problem. So we know that this is a known angle, 36.2 degrees. And we know the length of the hypotenuse. And we can then find the side of this. How? Because you know that the sine of 36.2 degrees has got to be equal to the opposite side divided by the hypotenuse. Opposite over hypotenuse, that's what the sine is. So A over C, but I know that C is 68, right? So this is going to be a number, this is a number, and so then I can solve for A, right? How do I solve for A? I need to multiply by 68. So A will be 68 multiplied by the sine of 36.2 degrees. So A is 68, and then the sine of 36.2 degrees is 0.591. And when you multiply this out, you get 40.2. And this is the answer for A. 40.2 what? Well, if it were 68 meters here, then the answer would be in meters. If it were centimeters, it would be in centimeters, and so on. So whatever distance units you're using. All right, so we can handle that. Now, let's take a look at what else can we solve for immediately. All right, well, we now know that this side is 40.2. How do we find the length of side B? Notice that the cosine involves the adjacent side, and we already know the hypotenuse, so we can write down right away that the cosine of 36.2 degrees is equal to the adjacent side of this angle, B, over its hypotenuse, which is 68. So because we were given the hypotenuse and we were given this angle, we can find A and B right away. So then B would be equal to 68 times the cosine of 36.2 degrees. Just multiply both sides by 68. And then what you get here is 68 times this cosine 36.2, you get 0.807, of course rounding. And when you take 68 times 0.807, you would get 54.9. And again, if it was in meters, then this would be 54.9 meters. If it was in centimeters, it would be in centimeters. So we're very close, right? Because we already had side B, side C, and now we've solved for side A and for side B. So we know the lengths of side A, B, and C, and we were given the measure of angle A. The measure of angle B was, C was already given at 90 degrees because it's a right triangle. So really, we only have one more angle that we want or that we need. And so what we can write down is we can say that the measure of angle A plus the measure of angle B plus the measure of angle C has got to equal 180 degrees for any right triangle, any triangle at all, actually. Now, measure of angle A was 36.2 degrees. Measure of angle B is what I don't know. And the measure of angle C here is 90 degrees. So put the 90 in here, and that's got to equal 180. So the way you solve this is you take the 180, you subtract 90, and then you subtract 36.2, and angle B works out to be 53.8 degrees. So we ask ourselves, have we solved the right triangle? There's 6 unknowns, 3 angles, 3 sides. Side A is 40.2, side B is 54.9, side C is 68. Angle A is 36.2, that's given. Angle B is 53.8, that's given. Angle C is 90 degrees, that's also given, because all of these problems in this lesson are all going to involve right triangles. So one of the angles is always already given. And so that's how you solve the problem. So for the rest of the problems, we're going to do similar things, but the sequence will be a little different depending on what sides I give you. You might tackle it in a different order. For instance, if you just look at what I gave you the angle and I gave you the side. So we knew this angle. Now I chose to do sine and then cosine, find the sides first, but I could have solved for the measure of angle B first if I wanted to, because I know that this plus this has to be 180. The first thing I could have done could have been this if I wanted to. It wouldn't have changed anything. So you might see a slightly different path through it, and that's fine. All right? All right, let's take a look at problem number 2. All right, so problem number 2. So I'm going to give you that the measure of angle B is 65.4 degrees. And I'm going to give you that side A is 2.35, whatever, millimeters, centimeters, nanometers, whatever it is. And we want to solve the triangle. We want to find all the other angles and all the other sides. So the first thing we do is what we always do, draw the triangle. Don't try to do this without drawing a triangle. You have a right angle right here, and always label everything. This is side A, this is side B, this is side C, this is side, well, angle A, B, and C, then side A, side B, and side C like this. Now we're given in the problem statement that B is 64, so I can put that here, or 65.4. And side A, which is this, is 2.35. So I recommend you just put that in the drawing. Now, how do we handle the rest of this thing, right? Well, again, I'm already given one of the angles here, which is this angle right here, 65.4 degrees. I know this is 90 degrees because it's a right triangle. So for this problem, I'll do it differently, and I will just find side A right away. Now we know all of the angle A right away. I know that all of these angles have to add up to 180 degrees. So straight away I can just say that angle A has got to be equal to 180 degrees minus the 90 degrees from here, and then minus this one, minus 65.4 degrees. So angle A, straight out of the gate, when you take 180 minus 90 minus 65.4, you get 24.6 degrees. And you don't have to do any sines or cosines for that. It's done. All right, next. What can we do next? Right, so we know that this angle right here is 24.6. So now that we have it oriented like this, we want to do our sine and cosine based on this angle over here, and it's going to be the sine of this angle is going to be the opposite side over the hypotenuse. The cosine will be the adjacent over the hypotenuse. But I need the hypotenuse, right? So I'm going to solve for the hypotenuse first. The sine of this angle has to be the opposite side over the hypotenuse. So I'm going to say that the sine of angle A, which is 24.6 degrees, has got to equal the opposite side, 2.35, over its hypotenuse, which is C, like this. Now we want to solve for the variable C. So if we multiply both by C, we'll get C multiplied by the sine of 24.6 degrees, and that's going to equal 2.35. And then if I divide over here, then C is equal to 2.35 divided by the sine of 24.6 degrees, right? And then what I get here is 2.35, and the sine of 24.6 degrees works out to be 0.416 in a calculator. And then 2.35 divided by this, you'll get 5.65. And that's the final answer for the value of C, or for the length of side C. So now I know what the hypotenuse is, and I'm going to write that down, 5.65. So I'll put 5.65. That's the length of side C. So how do I find the only unknown side, side B? Well, if I take a look at this angle, I can write down that the cosine of this angle, 24.6 degrees, has got to equal its adjacent side, which is side B, over its hypotenuse, which we now know, 5.65. So we needed that hypotenuse to be able to do it. We could do the cosine of this angle as being B over the hypotenuse, or we could look at this angle and say, okay, the sine of this angle would be its opposite side, B, divided by this. Either one would work, but just for giggles, to do something different, we can attack a problem differently. We can say that the Pythagorean theorem says C squared is A squared plus B squared. Because for a right triangle, you always have the Pythagorean theorem at your disposal. And we know the lengths of two of these sides, so we can always find the third one. So C is 5.65 squared, and A is 2.35, and B squared, or B is what we're trying to actually find there. So 5.65 squared is 31.92, and 2.35 squared is 5.52, plus B squared. And then B squared then is going to be this number minus the 5.52, and then you'll get 26.4 for this. And when you take the square root of both sides to get rid of this, what you'll get is you'll get plus and minus, but you discard the negative length. You can't have negative lengths on a triangle, 5.14. And so that's the length of side B. So let's double check ourselves that we solved everything. Side A is 2.35, side B is 5.14, side C is 5.65, okay? All three sides accounted for. Angle A is 2.64. Angle B was given at 65.4 degrees, and angle C is 90 degrees. So all three sides and all three angles. Now I encourage you, even though we use the Pythagorean theorem here, I just mostly did it for some variety. But if you go through and calculate this number and multiply by 5.65, you're going to get a value of B, which matches exactly 5.14, because everything should be self-consistent. Whether you use sine and cosine or whether you use Pythagorean theorem, as long as you're doing everything correctly, you'll always get the same answer. So check that out, and then let's go on to the next problem once you verify that you get the same answer. All right, now let's slide the board away and solve our last one of these problems. All right, let's say I give you, as a given, that it's a known quantity that angle B is 48.3 degrees. And you're also told that side B is 74.7 meters or whatever long. Solve the triangle. So, and this is a right triangle. Solve the right triangle. Well, the first thing you do is you draw the right triangle. Every one of these on my paper, I've written it down and I've drawn the right triangle, right? This is angle A, and this is angle B, and this is angle C. And so this is side A, and then this down here is side B, and so this is side C. And write down what you know. Angle B is 48.3 degrees. And then side B here, down here, is 74.7 meters or whatever it is. So what do we do first? Well, like I said, you really have choices. I mean, you can do whatever you want first, but I actually have two angles here. I have angle B right here, and I also have angle C. So I can immediately solve for angle A. So angle A is going to equal to 180 minus the 90-degree angle minus the other angle, 48.3. So angle A, when you take 180 minus 90 minus 48.3, you get 41.7 meter, or sorry, this is an angle, so it's degrees. 41.7 degrees, and that's the final answer for angle A. So let's write that down. Over here, we can just say 41.7, this is in degrees. All right, now we know side B, that's all we know. How can we proceed? If we take the cosine of this angle, it'll be the adjacent side, which we know, divided by the hypotenuse, which we don't know. But if I take the cosine of this angle, I can take the cosine of the angle, that'll be a number. Adjacent side is a number, so the hypotenuse is the only unknown number. So that makes sense, right? So I can do cosine of 41.7 degrees is equal to the adjacent side, 74.7, divided by the hypotenuse, which is unknown, and of course I can then solve this guy. So same thing, I can multiply by C to get rid of it. So C multiplied by the cosine of 41.7 degrees is 74.7. And then I'm going to divide by this, so I'll get 74.7 divided by the cosine of 41.7, like this. And whenever I take the cosine of 41.7, what I'm going to get is 74.7, and the cosine of this angle, 41.7, works out to be 0.747. And so when I divide this divided by this, I'm going to get exactly 100 for the length. And so that's 100 meters or whatever it is. Okay? So now let's go and see how can we find the length of the other side. So if we used, now we have the hypotenuse, which is 100, so I can put 100 here. And now I can use the same angle and use the sine, because the sine of this angle is going to be the opposite side divided by the hypotenuse. So the sine of 41.7 degrees is the opposite side, A, over the hypotenuse, which we just calculated to be 100. All right, calculated to be 100. All right, so what is the sine of 41.7? Well, what I can do is multiply, first of all, by 100, and basically turn it around and say that A is 100 multiplied by the sine of 41.7. Just multiply both sides of the equation by 100. So you have 100 multiplied by what is the sine of 41.7. That's the vertical side of kind of the projection of this hypotenuse onto the vertical side there. And you're going to get 0.665. Now, when I say it's the projection, when you take the sine and you multiply it by 100, that's the length you're getting is the projection of this hypotenuse onto the vertical side. This ratio is basically, if the hypotenuse were 1, like in a unit circle, then the sine, which is 0.665, is telling you the vertical component of a triangle with a hypotenuse of 1 in a unit circle is going to be this high. So you take that ratio, multiply by 100, and then you get the height of this triangle when our hypotenuse is exactly 100. Okay, so it's like the sine and the cosine is, if it's a unit circle with a hypotenuse of 1, the sine gives you the vertical projection, the cosine gives you the horizontal projection. If the hypotenuse were 1, this is how much of it would be in the vertical direction, times 100, then we get 0.665 times 100, 66.5 meters or whatever it is. Now let's double check ourselves. For the sides, A is 66.5, B is 74.7, C is 100. And for the angles, angle A, 41.7, angle B, 48.3, angle C is 90. So we've solved the triangle. Now I want to tell you, as I've been saying many times, that you can solve these multiple ways. You don't have to use the sine to solve this. So if you just cover this up and say, let's don't do this. How do we figure out, we're trying to find this side right here. How do we do that? Well, what you could do is you could say the tangent of this angle is the opposite side divided by the adjacent side. And that would work too, because if we take the tangent of this angle and the calculator, we'll get a number, and that's equal to unknown divided by known. You don't need the hypotenuse, in other words, to figure it out. So I encourage you to do that. You could say tangent of this angle equals A over 74.7, and then you solve for A, you're going to get exactly the same number as we get here. So that was the idea of solving a triangle. We want 3 angles, we want 3 sides, and it turns out that if I give you any 3 pieces of information, either 2 sides and an angle, or 2 angles on a side, or 3 angles, or 3 sides, if I give you 3 pieces of information, then using trig, you will automatically be able to calculate the remaining 3 unknown pieces. So we're doing it here just for triangles to get you comfortable with it, but the reason we do it is because if you're surveying land or calculating, anything, the distance to the moon, if you know the angles, you know one of the sides, if you have 3 pieces of information, you can calculate the others. And so we use it all the time to triangulate distances, how far away something is, the angle, all these things we use in real life to calculate where things are on a map, for instance. So solve these yourself. When you feel like you understand what you're doing, follow me on. We have a part 2 of solving right triangles.